Monday. Happy sunny Monday. I guess we have about 50%, maybe less, 50%-ish turnout today. Anybody else cycle this morning into the university? Am I the only cyclist? Oh, I'm surprised. Luckily, it's all downhill on the way in. But I'm cycling in this weather, you know, with the wind and the rain beating down, and the rear axle somehow came loose on my bike, and it broke. Like, I was like, why is it not pedaling?
So you walk?
It's all downhill, so I just stayed on the bike.
Okay.
And it was cruising the whole time.
Yeah.
Yeah, it was slippery. It felt a little bit hazardous, and I had goggles on. I'm sure I looked very cool. I'm sure. Any questions about assignment 2 before we start? So it looks like at least 2 people are done. I saw already. Looks like that. So maybe it's too easy, the assignment. I'm going to make it harder next time. I still have some score sheets from assignment 1, so if you didn't pick up a score sheet from assignment 1 and you want to pick up a score sheet from assignment 1, you can do so after the lecture. So this is a so-called real flow visualization. And we're not going to talk about real flow visualization very much. What I mean by real is experimental. So that is real fluid flow, and that is somebody trying to visualize the fluid flow. So that's a block, right? And the fluid is constrained between 2 plates, so it's just a thin layer of fluid. And then some substance has been put in, so we can track the motion of the fluid. And it's fascinating, right? I can see some things, but it's also very difficult, right? It's very difficult to see what's happening there, even under all these constraints. There's a light in the back, right, projecting forward to make it nice and clear. And even with all that fancy equipment, it is difficult to see what's happening. You can see some things. And so we're going to see the same kind of data in the simulation world as well, and it'll be easier to visualize. But that's just a fun animation of what real flow visualization. And I have a friend he's called Harry Ye at Oregon State University, and he does real fluid flow. He has a big, expensive wave tank, and he makes artificial waves and studies the waves. And it costs a lot of money. It's definitely a good investment, though. It's when you see the energy that's stored in those waves, right? Seems like a very good investment. So last time we started to talk about flow visualization. We changed topics from volume visualization to flow visualization. Right? We talked about what it is, magnitude versus direction, these different subcategories of flow visualization. That the data comes from simulation, flow measurements. So that video we just saw was flow measurements using optical measurement techniques, which we're only going to talk about for a minute or two. Right, simulation, measurement, and modeling. We mentioned CFD. We're going to keep mentioning that. The data that we see in all the videos and the examples comes from CFD. And then we looked at the plane, the animation of the plane, the real flow visualization again, some different examples. 2D versus surfaces versus 3D, steady versus time dependent, some historical data set growth, the growth of data sets historically over time, and then we finished here on this example of direct versus geometric FlowVis. This is direct FlowVis, this is geometric FlowVis. So one of the things I mentioned is there's complete coverage of the flow here, more or less. At least it's very visually complicated. And there's occlusion. Here it's more visually coherent. Right? We get a continuous image of the flow. However, it's not complete coverage. So we have to figure out where to place those stream ribbons. Like how did the position of those stream ribbons derive itself, or how was it derived? And we will talk about that, by the way. So just a very quick look into the world of experimental FlowVis. We're not really going to study experimental FlowVis, but it's still fun to mention. Right? These are all images from experimental FlowVis. This is airflow, right? And those are instruments trying to measure the velocity. And these are fluid flow examples, right? This is dye being injected into some volumetric flow. And there are particles in this flow being tracked. So a camera with a high frame rate takes photos of the flow and tracks the particles over time and builds a correspondence between the particles, between two frames. So you know the amount of time that passed between the two images, the two photographs, and then you know the displacement. You can measure the displacement in space. And if you can measure the displacement in space and then divide that by the time, then you have the velocity. So you can measure the velocity. Right. And somebody asked a question about instruments that are used to measure flow, like how is that possible? You can Google something called the 5-hole probe, and that's one of the instruments that's used to measure velocity, right? And the world of automotive engineering is a very popular world for trying to understand flow and how it interacts with the car frame or the body of the car. And you can go to conferences. It's its own field. It's its own profession, right? Fluid mechanics. You can go to conferences on fluid mechanics. You can dedicate your career to studying that. This is I think the last slide that we have on the topic. One of the techniques used to study flow in the experimental world is called, if I can pronounce it, particle image velocimetry. I don't know why I always struggle with that word. So that's the method I just described. Tracking particles over time by taking photographs of them and then making the correspondence. Right? PIV, an optical method used to measure velocities and related properties of fluids. The fluid is seeded with particles which for the purposes of PIV are generally assumed to be faithfully follow the flow dynamics. It is the motion of these seeding particles that is used to calculate velocity information. Right, so if you can track displacement over time, dx over dt, then you can derive velocity. Right, and these are just some of the concepts behind experimental flow visualization. Right, we have wind tunnels at Swansea University. You can inject particles into flow. You can inject smoke into flow. Right, we saw an example of that last time. You can inject liquid as a dye, right, and so on. And then you take pictures with a high-speed camera and you try to figure out the correspondence. It sounds complicated, and I think it is complicated. Here's an example that's one of the reasons. I mean, there are lots of great reasons to study fluid flow, right? There's a big group here at Swansea University developing marine turbines. I think we mentioned that already. Right? That's a great application of flow visualization. Wouldn't it be great if we could derive all our energy from the ocean currents or the tide? That would be really great. Here's another application, and we saw this already in one of the videos. When a plane flies, the air that passes the wing starts to spiral into vortices, right? Which can be dangerous if you happen to be on a plane right behind another plane, right? Because you could fly into those vortices and maybe something bad happens, right? So vortices can be dangerous. This is a schematic diagram of what they look like, right? So that's a plane, and this is a schematic diagram of the vortices that are created behind the wingtips, right? So there's a drop-off and there's a rotational flow inwards with a counterclockwise, a clockwise direction, right? So this one's called upwash and this one's called downwash. And the consequences are that some time has to elapse between planes landing and planes departing from an airport, right? So this is one of the factors that's taken into consideration. And the larger the plane is, the more distance that's needed between successive planes, both on the takeoff and the landing, right? And this is a diagram that shows a little bit about the distances that the planes need to maintain between departing and landing. Here's an example that shows the development of wings in an experimental setup in a wind tunnel. So lots of people spend lots of time trying to optimize wings, including people at Swansea University. I did meet a professor at Swansea University that was trying to optimize wing design and showing me different examples. Well, he was trying to show the behavior of the flow past the wing, but he was struggling, right? Because he didn't know really about state-of-the-art flow visualization. This is another example. Well, it's the same example, but now it's visualized in a different way. So there are slices or cross-sections of the flow taken at different times. And then the velocity vectors are projected onto the slices and color-coded so you can visualize velocity magnitude on the slices. And then these special lines are extracted in three-dimensional space, right? Those are called vortex core lines. Does anybody remember where we saw those already? I guess for a rainy Monday morning, that's a very difficult question. Anybody remember where we saw those vortex core lines already? We saw them in the cooling jacket. I don't know if anybody remembers that slide with the cooling jacket, the 4 different cooling jackets. This is the feature-based flow visualization example. And that's a close-up of what that looks like. Trying to study the wind behind the wingtips. And that's also another visualization example. This is trying to emphasize the time-dependent nature of the flow, right? So this is the time the closest to the wingtip, let's say. This is a little bit further back and further back and further back. So you can see it sort of comes down the flow. And then there's another depiction of the same thing with streamlines on the slices. Right, so there's one thing that's happening here, by the way, is that the flow is projected onto this 2D plane. There is no two-dimensional flow in real life, right? It's just something to keep in mind that there's a third component pointing in and out of the plane, the two-dimensional plane, not the aeroplane. Okay, let's look at some, make sure we've seen all the demos. So what is this one? Okay, that one's not that exciting, I think. Let's just quickly have a look at, assuming my laptop can actually play it. Okay, that's good. That's the plane demo. Now we can watch it again and we can appreciate it a little bit more now that we know what we're trying to visualize, the vortices behind the wingtips. So that's what they're trying to visualize with that smoke. Very expensive experiment. And these are some of the examples we looked at already. So now you know a little bit more already. You don't know all the details, but you know a little bit. You know this is texture-based flow visualization, for example, even though we haven't studied it. You know that this is CFD simulation data. So this is the same data, but now visualized with streamlines or short streamlines. It's actually the same data. And the depth is included. So that's the texture-based flow visualization again, and that's the diesel engine simulation, and it's projected onto a slice. That's simulation of dye injection. It's the same data that we just saw. This is extending into boundary surfaces, so those were all 2D slices. So now we look at the boundary surfaces. This is texture-based flow visualization again at the boundary surface. And the texture is being animated in the direction of the flow, so we can see the downstream direction. There's a copy of this on YouTube, by the way, if you'd like to slow it down. The comments are very quick, so it's difficult to read the comments while you're looking at it in real time, but if you can watch it on YouTube and slow it down so you can read the comments. Those are timelines, so those are curves that are seated at the same time point, but at different locations. Those are three-dimensional streamlines. So now we've gone from surfaces to volumetric data, so 3D data instead of just slices of surfaces. So those are three-dimensional streamlines, and they're animated, right? And that's a seating plane, by the way, seating them. We're going to talk about streamline seating very soon. And that's a combination of an isosurface and three-dimensional streamlines. And now you know what an isosurface is. That's another isosurface of pressure, three-dimensional streamlines, and then the 2D texture in the background, all combined together. Okay. So let's look at the next parts. don't know if I should put this one or this one. Just see. Just quickly have a look. I know that's okay. Yeah, I guess we'll do this one. So here is another demo. We're going to look at some glyphs. This is an example of using glyphs for flow visualization. And here is the next sentence. So this is FlowVis part 2. There's our favorite cooling jacket again. And those are glyphs used to visualize the flow of the cooling jacket. So trying to position the glyphs is a challenge. And that's what this video is about. Right, this is the standard visualization technique. The standard visualization technique is to take a vector glyph, which is an arrow that points in the direction of the flow, and just attach an arrow to that position to every velocity. But you can see that that's not ideal, right? Because the arrows are unevenly distributed, right? So the arrows are more sparse here and more dense here. So we can't really see them here because they're all overlapping. They're too dense, right? And then they're sparse up there. And that has nothing to do with the flow. The sparseness and the density of the vector glyphs, that's about the mesh that's used to simulate the flow. So that's not a reflection of the flow, actually. So that's just taking a glyph and attaching it to every sample, every vector sample. And that's called hedgehog visualization. And that's what everybody uses in practice, which is too bad. But it would be nice if we could come up with a way to place the glyphs in space that makes things a little bit clearer, or the flow easier to perceive. So that's what we worked on. So that's a grid being used to place the glyphs. And the resolution of the grid is controlled by the user. So the user can generate sparse representations of the flow or dense representations of the flow, and then actually interact with the grid, rotating it and sliding it around, and so on. And the vector glyphs are at the center, positioned at the center of each grid. So this is the same simulation data that we've seen a few times already. Right, and this is 2 grids of different resolutions, and that's a more higher resolution grid being controlled by the user and changing the resolution if they're interested in getting more detail and rotating, that sort of thing. And then it's easier to see the flow, rather than trying to attach them to every sample. It's also faster than the other hedgehog visualization, because the hedgehog visualization, you're rendering thousands of extra glyphs, right, which can be slow. There's a copy of that one on YouTube as well. So let's look at the next part. Everybody have a copy of the notes? Those are the extra copies. Everybody sign the attendance register. Any questions about the first part? I see the audience is quiet today, so I might have to stop quizzing you. I took a class, an operating systems class, as a master's student, and the professor gave surprise quizzes at the beginning of every lecture about the previous lecture. It was very intense. It's like, Okay, you walk in. Okay, surprise quiz. You have 10 minutes to write this quiz. It was really intense. So we're going to start that here, I think, too. Okay, so let's look at part 2 of flow visualization. So we're going to talk about FlowVis with arrows, and then we're going to talk about numerical integration, and we're going to talk about streamlines. Right, so numerical integration is the technique used to compute streamlines, how to compute those curves. So this is a direct flow visualization, just like the one we saw in the video. This is a two-dimensional vector field, and there's an arrow placed in every vector in the two-dimensional field, right? And that's a visualization of the two-dimensional flow, right? Very common. So does anybody see any limitations with this kind of visualization? Any way we could improve that? Ala, what do you think? Anyways, is there anything missing? Is there some way we can improve this visualization?
Colors.
Color, yeah, it's missing color. We could use color to encode something. Right? That would be nice. Anything else that could be added to improve it? The third dimension? Yeah, exactly. The vectors are combined to the two-dimensional plane. Right? So that's called dimension reduction when you take away one of the dimensions. Right, so color is missing. Another thing that's sort of missing or could be improved is all the arrows are the same length. Right, so it makes it look like the flow is uniform. Right, that's what this phrase normalized means, normalized arrows. It means they're all the same length. They've all been resized or scaled to be of unit length. So it makes it look like the flow is uniform. But that's not true. This flow, I just know from experience, this flow is slower than this flow. Right? So the flow at the center of a vortex is slow. Right? And so, by the way, it's frequently used. We are, like I mentioned in the last lecture, we are trying to connect the arrows in our brains. We're actually trying to connect them, even if we don't notice it consciously. But our mind is trying to connect the arrows. Right, these are some more examples. Right, these arrows are scaled, but they're still hard to see. Right, that's a very low quality image. There's color that's been added. Those are very low quality images. Luckily, we have the video to demonstrate some of these things. We could add shading to help with the three-dimensional perception. By the way, this arrow and that arrow look exactly the same, even though they're pointing in different directions. So that's the arrow being projected down, right? And it's pointing forward. That's the same arrow, but it's projected down and backwards. So does everybody see that those two blue arrows look identical, but they're pointing in different directions? And it's just difficult to perceive one-dimensional objects in 3D space. We can add some shading information to help with that. But it's generally true. Rotation is another thing that helps a lot. So those are some more examples of vector glyphs or vector arrows. these are confined to a two-dimensional slice, so we can see a vortex there, and they're also scaled, so we can see higher velocity magnitude here, like in very, very low velocity magnitude here. Here's some very low quality imagery with some arrows that have the third dimension, right? And there's another example with the meteorological data. So that's a little bit about arrows. Do I have anything about arrows there? Except that we saw our vector glyph demo already. Now we're going to talk about streamlines, how to compute streamlines. Does anybody remember the lines that or the curves we already talked about computing? We already talked about an algorithm to compute curves. They weren't called streamlines, though. They were a different kind of curve. Anybody remember?
Blood was passing through the tissues. You have shown
Yeah,
in the previous lecture.
in the previous lecture,
Not just the previous, before 2 lectures.
it was a blood flow example. Oh, you mean the contours?
Yes.
The contours, okay. Contours I wouldn't say are necessarily the same thing as curves. Contours are like boundary surfaces, or the edges of surfaces. But we did talk about another kind of curve, and we talked about an algorithm to compute those curves already. Now we're going to talk about an algorithm to compute curves again, but a different kind of curve called a streamline. But there's a duality between these two algorithms. They're connected. They're related to each other. How about Jin Long Du? Is Jin Long Du here? Where is it? Okay. What do you think? Do you remember any previous curves in any of the previous lectures? Any algorithms for computing curves? Can anybody help him out? Yes, nice. What's your name again? Dennis. Well done, Dennis. Good memory. The isocontours are another kind of curve, right, that we computed. And these are not the same kind of curve, but they are related to each other. They're orthogonal to one another. So a streamline is a curve that's everywhere always tangent to the vector field, right? We can't say that about the isocontour. An isocontour is a curve that's of constant scalar value, so that's a difference, right? One's for scalar fields and one's for vector fields. And I won't go into much detail about the theory, integration theory, because only one person here has taken calculus, if I understand correctly, or 2 people. Has anybody else taken calculus before? So this would only make sense if you've taken calculus. One thing that's very interesting, though, even if you haven't taken calculus, if you have taken calculus, it's even more interesting. But even if you haven't taken calculus, has anybody ever seen that integration symbol before? Even if you haven't, yeah. So I wish somebody had told me this when I was... The mathematics professors did try to tell me, but I never quite got it. But this integration symbol is really a special kind of addition. Actually, that's what it is. It's adding up something. It's adding up a quantity. I wish I had known that back when I was taking calculus, or I had that interpretation. And it's a kind of continuous addition or analog addition. And this maps to a different symbol in the world of computer science. So this is the world of mathematics, which deals with continuous quantities. Does anybody know what symbol this maps to in computer science? How we represent this addition in computer science? It's a very difficult question. I wouldn't necessarily expect you to know that. But this is a sigma. The sigma, the Greek sigma symbol in computer science, or it's the computer science equivalent of this integration symbol for mathematics. This is the continuous version of addition, and the computer science version of addition with the sigma is the discrete addition, so you'd call it discrete mathematics. And the sigma is an approximation of the continuous version of the addition or integration, as it's called. I wish I would have loved to have known that from the very beginning. Nobody's ever explained that to me, ever, actually. But now you have an explanation. It's not imperative that you understand that, by the way. It's not imperative. It's just nice to know. It's nice. Because those mathematical symbols are a little bit mysterious. So in the world of mathematics, we solve an integral analytically with lots of different techniques. Sometimes it works and sometimes it's not even possible. But if we want to compute an actual number, we need a discrete representation. We need a way to add up the numbers using discrete mathematics. And that's what we're going to do. We're going to approximate the solution to this theoretical addition or this analytical addition, also called integration. Integration over the flow field. So we're adding up, that v is velocity, by the way, and that s is position. So we're going to approximate the solution of computing points along a streamline with something called Euler integration. Right? So this means the next point on a streamline is the previous point plus the velocity at that point multiplied by a very small amount of time. That's how we interpret that. And we're going to go into that in detail right now. How many people here like mathematics? I know you do, Anton. Have you seen this before? Okay, Anton's already seen this. If I make a mistake, don't say it too loud. So this is we're going to use this data set as an example. This is an analytical data set just like Sally. Right? Remember Sally, we input a position and we get back a velocity. The same is true about this example. So if we input a position, for example, we input the value of 1 for y, that corresponds to, we have a multiplier here, -1. So we multiply -1 times 1, we get -1. So if we go to y, which is 1, and then we multiply it by -1, we get the x velocity, the x component of the velocity. So we get -1 for a velocity value at that position. Does everybody see that? Now, for the y component of the velocity at this position, 1, 0, 1, x is 0. So if we plug in 0, 0 divided by 2, we get 0. So the velocity at this position is -1, right? So it's pointing in the -1 direction, and there's no y component to the velocity. That's a little bit confusing, isn't it? But that's how we get the velocity. That's the formula for the velocity at any point in the vector field. We plug in the position, and then we get the velocity, the x component of the velocity and the y component of the velocity back. And these are just a few of the examples, right? If we plug in this position, the velocity points here. If we plug in this position, the velocity points there, and so on. So the flow looks like this. It looks like a circular pattern, and it's counterclockwise or anti-clockwise, as you would say here. Right. Now the question we want to answer is, we know how to visualize the flow with these arrows, right? This is just an arrow with an x component of -1, 0, and a y component of 0, so it points that way. Wouldn't it be nice if we could visualize this flow with streamlines? Curves that are everywhere tangent to the flow. That would be nice, right? So that's what we're actually talking about now, how to do that. Assuming the windows don't crash and the storm blow us away.
It happened in South England.
Yeah? There was some sort of accident?
I have a friend who lives there.
Where?
In, next to Brighton.
Okay, that was like last night or something?
2 days.
2 days ago, okay.
It is a storm. Yeah.
Swansea will be underwater in a few years. It's a good thing Swansea's on a hill. I live at the top of a hill, so my house is going to be last. I'll have to get a boat or something. So in order to compute a streamline, we're trying to compute those points along the streamline. Right? So imagine we start computing our streamline right here. This is what we call a starting point for the streamline, or a seed point for the streamline. How do we compute the next point on the streamline? If we can compute the next point given the previous point, then we can always compute our streamline, right? It's always just given a point, how do we compute the next point, right? And then we recurse. Given this point, how do we compute the next point, and so on. But it's always the same. It's always the same, right? And we already saw the formula, by the way. Just as a refresher, the formula looks like this. To get the next point, we start from the previous point. We take the velocity at that previous point, and we multiply it. That's a multiplication by a small time interval amount of time. It's very intuitive. Just take the velocity and multiply it by something, and we push to the next position. It's very intuitive. It's what you would think. If you had to invent a way to do it, that's what you would invent. So we take this point, and then we have to derive the velocity vector at that point. So that point is 0 minus 1. So to get the x component of the velocity, which is here, we take the 0, or the minus 1, which is y. Y is minus 1. We take minus 1 and we multiply it by minus 1. Right? It's the opposite of minus 1. So minus 1 times minus 1 is 1. 1. Yeah, it gets confusing. So if you see this on the tests, make sure you write every step down, yeah? Not that this is going to be on the test or anything. It's very easy to mess this up. It's simple, but it's still easy to mess up. And the reason it's easy to mess up, by the way, the reason you're not used to this, is because there are two components. There's an x and a y here. You're not used to multiplying, adding, and subtracting vector quantities. You're not used to that. You haven't had much practice with that. So minus 1 times minus 1 is 1. So the x component of the velocity is 1. And that's written down here, right? And that's pointing this way. The y component is x divided by 2. Well, x here is 0. So 0 divided by 2 is 0. So the y component of the velocity is 0, and that's notated here. So we have 1, 0. So the vector at that position is pointing this way. Right? That's the first step of how to do this. Now, the multiplier we're going to use, the time interval, we're just going to give it to you. It's called a half in this example. It's just, we're going to multiply this vector by a half, a time of 1/2 of a unit. Right, so if we multiply 1/2 times 1, what's 1/2 times 1? 1/2. It's 1/2. And then 1/2 times 0 is 0. So that's the next point on the streamline. So we add the 1/2 0. So we started here, and then we add a half unit in the x direction and 0 in the y direction. And we have the next point on the streamline. So it was those two steps. Getting the velocity component and then multiplying it by a half. Just those two steps, but it's kind of confusing. And then we take that information and we add it to the previous position to get the next point on the streamline. And now we have our next point, which is 1/2 minus 1 here. And then we do the same thing. We evaluate the velocity there to get the next component. So the next component is 1 and 1/4, right? And that's this vector, by the way. So the next point along the streamline is we multiply that vector by a half, and we end up with a point right here. Right here. And we do the same thing over and over and over again to compute the whole streamline, right? We evaluate the velocity. So here we're at 1 minus 7/8, and then we add it. We evaluate the velocity, and then we compute the next point on the streamline. And the numbers start to get very awkward at this point, so you want to use a calculator actually to start computing the numbers. But that's the next point, and then the next point, and those are more points along the streamline, more points, and more points. So that's how we compute a streamline. Yeah. And I know this is confusing, and a student asked a question about this for the test last year. So I made a little tutorial with a whiteboard and a marker, like doing it by hand on the whiteboard. It's also on YouTube, so you can check it out if you got lost here.
Is it like we have to memorize the formula?
No, you generally, since I'm very poor at memorization, I don't inflict that on you guys. But you might be given a formula, and then you have to do something with it, like Here's the Euler integrator. Compute some streamline points, for example, with this Euler integrator. Any questions about that? It is confusing. It's probably something you have to look at again to understand. One thing I will mention though is it's very intuitive. It's like, here's your position, there's a flow pointing this way, so if you're a massless particle sitting here, you're going to get pushed that way a little bit. And if you're here, and you're a massless particle sitting here, you're going to get pushed this way a little bit, because the flow is moving like this, right? So it's just pushing the position around according to the flow. It's very intuitive in terms of like just thinking about it. Any questions about that? I think we're out of time. Yes, so happy Monday morning. Let's all go to the beach. I'll meet you at the beach.